So our first talk is going to be by a graduate student, Elizabeth Melton, and she's going to tell us how we can save the world from asteroids without help from Bruce Willis.
Okay, so we've all seen the movies where you have all the people running around and screaming because an asteroid's about to hit the Earth. Armageddon was not the first movie to use this. The first movie was The Day the Sky Exploded in 1958. It is an Italian sci-fi film. There are lots of different films that use this. Armageddon, Deep Impact, Asteroid, Your Name, Starship Troopers, Monsters vs. Aliens. So, what can we do when science fiction becomes a reality? You know, they had little flip phones on Star Trek way before we ever got cell phones. So, it's all coming. Aha! Invaders from above. There is a section of NASA called the Planetary Defense Coordination Office. Its job is to search for and track near-Earth objects, asteroids and comets. Here you can see the objects that NEOWISE has found over a 3-year period. That is the Near-Earth Object Wide Infrared Survey Explorer. The sun is in the middle. The Earth here is in the light blue. The green are potentially hazardous asteroids and objects, comets. Yellow is comets, and gray are all the other little asteroids out there, mostly in the asteroid belt beyond Mars. Now, near-Earth objects are defined as coming within 121 miles of the sun, or 21 million miles, or 30 million miles of the Earth's orbit. That sounds like a nice, comfortable room, but space is huge. Now, these objects look really close together, especially out here in the asteroid belt, but there's actually a lot more space than you would think. The average distance between asteroids and the asteroid belt is about 1 million to 3 million miles. Asteroids in movies. Yeah. Will it do it? Come on. Aha! I win. Okay. I love that clip because it is the least dramatic asteroid impact ever. And completely unrealistic. So, you do find asteroids by looking for them in movies, but you have to make that movie. So first, you take lots of pictures of the night sky, and then you line up the background stars in each picture. Stars do move, but they move very, very slowly from our perspective. In about 10,000 to 100,000 years, the constellations as we know it are going to be unrecognizable. But since they aren't going to change over a night, or a month, or even a year, we can do this. So you line up all the background stars in each picture, and then you just flip through the pictures. You make a movie, and you look for what moves. If you look here, you can see this little purple and red guy circled, and that is showing you an asteroid found by the Catalina Sky Survey. Once you've done that, celebrate and repeat. So, we found our asteroids. Now we got to worry about what they're going to do when they hit the Earth. How much damage an asteroid is going to cause depends a lot on how it's made. You got rocky asteroids, metallic asteroids, asteroids that are basically big piles of pebbles held together by gravity, asteroids that are much more solid. Size is a really big factor, and that's something we're going to focus on a little bit here. So this shows you what kind of damage and how many casualties you might expect to see from an asteroid of a given size. There's a line here at about 50 meters. Below that, the asteroid is most likely going to break up in the air as an airburst. Not guaranteed. It says only airburst. It is not guaranteed. It depends on a lot of factors of how the asteroid enters our atmosphere. Between 98 to 164 feet. Those are basically your bottom cutoffs for asteroid size and diameters for being able to hit the ground. At 460 feet, about 150 meters here, a football field and a half length. That's when you start really getting worried about asteroids. Now, that sounds like a really big object coming at you to start getting worried, but that's when your asteroid is going to start having regional effects, and you're going to see lots of ground damage. At about 3 football field lengths, a little bit more, 984 feet, you're going to get sub-global effects. So it might affect the area of like a country or a state. Larger than that, at about 0.6 miles, 1 kilometer, for you Pokemon Go fans, you're going to start getting global effects from the impact. This does not mean everybody would die, but it does mean everybody would notice. You can see here my diameter here only goes up to 400 feet. What you get also depends on where you hit. If you land in the middle of the Great Plains, you're probably not going to get a tsunami, no matter how big you are. But if you land in the ocean, which you have a much better chance of, could cause a tsunami. There's lots of different damages that you can get. So, how many of these guys are out there? This shows you how many asteroids are out there based on size. This is from JPL. These are 1 kilometer or more asteroids. These are your asteroids that are going to cause global effects. We believe that we have found 90% of the 1 kilometer near-Earth asteroids that are out there. 140 kilometers, 140 meters plus. That is the size that NASA's goal is to find all of them. We believe there are about 25,000 of those asteroids out there. We believe that we still have 74% left to find. Right, your congressman? We want to find them all. And then, of course, there are lots more smaller asteroids than these ones that are just going to cause regional effects. The smaller you are, the more there are. We are finding asteroids that are larger than 140 meters, about a football field and a half, at a rate of about 500 per year at the moment. So, that's great. I threw a bunch of numbers at you. I'm going to show you here this video from Business Insider. It gives you a little bit more of an idea of how much damage is caused by asteroids. They're using the Purdue Impact Calculator here. This one's 40 feet. It's a solid iron asteroid moving at 12 miles per second. And these are all if these asteroids hit New York City. There's only 3 of them, so bear in with me. So that's how big your impact crater would be. Get buildings destroyed for about 3.5 miles around impact. Let's up the ante. Asteroid 2 here is 3 football feet, 900 feet, 3 football yard fields, whatever. I don't play football. This asteroid is much less dense. It is only rock. If it hit, how big the impact crater would be, buildings destroyed, your clothing would actually ignite from the thermal energy release and first-degree burns.
That's terrible.
All the way halfway through New Jersey. Asteroid 3, 1.2 miles, 2 kilometers large. It's 5 Empire State Buildings. If it were to hit New York, again, this one is just rock. Just. This is one where you would see global impacts. So there's the impact crater, 7 magnitude earthquake, buildings destroyed as far as Massachusetts, and you get first degree burns as far as Canada and here in State College. So let's all hope a 1.2 mile asteroid does not hit New York City. Fingers crossed. There are a number of methods out there that have been proposed for saving us from these asteroids. Most of them rely on Newton's third law. Newton's third law of motion states that for every action there is an equal and opposite reaction. Like lighting a rocket engine and forcing the heated gas to go out a small area pushes the rocket in the opposite direction. You have action and a reaction. It's not just action, it also works with forces. This is why you all can sit in your chair. Earth is pulling you down due to gravity. but the chair is also pushing you back up. Action and reaction. This is a common theme that you're going to see within all of these. Let's get out the most popular one out of the way first. Nukes. We got them. Let's use them. You have two options. If you're going to use nukes, you can either blast it or you can fry it. Let's look at blasting it first. So blasting it, obviously the goal would be to destroy the asteroid and vaporize it. But as you see in my highly scientific picture over here, if you're going to explode something, you're going to get all these little fragments around it. So one of the things you have to really be worried about is this buckshot effect and also radiation because it's nuclear weapons. The second option you have is frying it. So frying it wouldn't be so much exploding the nuclear weapon on or inside the asteroid, but exploding it near the asteroid and heating up one half of the asteroid. If you do that, you would vaporize material on one half of the asteroid, where my little flames are, and the heat from the vaporization would push out on the asteroid and cause the asteroid to go in the other direction. So you would be near to the side of the asteroid, and you would exert a force in the opposite direction. It doesn't actually hit. Yes, we can do that, but there are a lot of other better options out there. One of them, we can play pool. When you play pool, you actually exert a force on the stationary ball by pushing it with another ball. So you can do that with a spacecraft. You can purposely crash a craft into the asteroid. At 60 kilometers per second, if you were to crash something into the asteroid, you could impart a kinetic energy of 1.8 billion joules per kilogram the spacecraft crashed. Now, you are talking about moving a very, very large rock. Yes, that's a lot of energy, but it's a very, very large rock. You're telling to go somewhere else. You just need time, though. If you can spot an asteroid 10 years in advance from when it's going to cross the Earth's orbit, a change in velocity of 1 centimeter per second, or 0.02 miles per hour, can give us a nice wide comfort zone for passing each other. So, this is what you could do. There you go. Asteroid deflection. If you don't like the destructive path so much, you can always go green and use solar power. Solar sails are a very large area of research to be used right now. How they work is the sun is constantly emitting a solar wind. It is made of photons and particles, and the solar sail actually uses radiation pressure. The energy imparted on the sail by the photons inside the solar wind push on the sail. So if you can attach one of these solar sails to an asteroid, you could actually push it and move it out of the way. There is one bit of a problem though. Asteroids tend to spin. So you'd have to attach that sail very, very carefully so it didn't get tangled up. Or you can use the spin, also using solar power. So asteroids tend to spin and they have what's called a Yarkovsky effect. So as the asteroid absorbs energy, it also radiates that energy into space in the form of heat. Because it is spinning, it doesn't radiate it into the same place. It absorbs the energy in the morning and radiates it in the afternoon. If you think about this, this also applies on Earth. You know it's cooler in the morning and it's warmer in the afternoon. It's not hottest at noon when you're actually pointing directly towards the sun. It's hottest in the afternoon. As you're pointing away from the sun, the Earth tends to radiate it more in the different direction. This radiation of the heat is actually pushing the asteroid in the opposite direction. It's called the Yarkovsky effect. And it gives a net force on the orbit. So, if you can somehow change how the sunlight is absorbed by the asteroid and re-radiated, then you can change the orbit. How would you do this? Well, this guy, graduate student at MIT, Sung-Woo Park, in 2012 won a Move an Asteroid technical paper competition by proposing to do this with paintball clouds out in space. Sounds crazy, but here he's using the asteroid Aphos. Sorry, I can't pronounce anything. Aphos, And as you can see, as it gets, he proposes making clouds of pink balls and pellets in space and coating the asteroid with white paint. And it means that you would change how much it can absorb from the sun, and so you would change how much of a Yarkovsky push that it feels as it goes around the sun. So, he estimates that you would need about 20 years or so to get this right, but it is definitely a very viable option. As a side note, you can't just run out to Home Depot and grab some paint and start slinging it at the asteroid. Water-based and oil-based paints would actually vaporize in space, so you'd have to use a chalk duster pellet. I thought that's interesting. So, we are heating things up with the sun. This picture is actually not an asteroid. It's a comet. It is Comet 67P. It was flown by in the Rosetta mission by the European Space Agency. What you can see here is you can actually see that the heat from the sun is melting part of this comet, vaporizing the material and causing it to outgas. You can see those here. You can see that here. Outgassing on the material, as we saw with the fry it with the nukes, exerts a force on the asteroid or object in the opposite direction. Well, so the sun does that. Why can't we? We can use lasers on a spacecraft or use mirrors to redirect energy from the sun and use it to vaporize material on one side of an asteroid in order to cause it to change directions. Sorry, I stole bits of clips. So far we've been attacking the asteroid. We've been working on changing the asteroid, but what if we just need to think around the problem? Out in space, gravity is king. All objects are gravitationally attracted to one another. You are attracting the Earth just as much as the Earth is attracting you. The Earth doesn't move up to you, that you notice, because it is so much bigger. If you were to drop a pencil at a height of about 6 feet, you can do all the nice little math, but the pencil moves towards the Earth, and the Earth moves towards the pencil. Now, the pencil moves about 6 feet towards the Earth. And I say about because the Earth moves 1/9 trillionths of a width of a proton towards the pencil. But it does move because things are gravitationally attracted to each other. If you wanted to move the Earth 1 hair width using a pencil, you would have to drop it from about 20 Earths out. But you could do it. So gravity is king. So even using a small space probe next to an asteroid, we could use it like a gravitational tractor pull. By flying a small spacecraft near an asteroid, such that it's not going to crash into the asteroid itself, we could actually use it to pull the asteroid out of orbit. Again, all these methods rely on early detection. The longer we have to pull, the better we are. And so you can actually just use these spacecraft to slowly pull the asteroid into a new orbit. Now, there are just a couple more, a little bit more out there techniques. One involves, again, this idea of equal and opposite reactions. When you have an automatic ball feeder, right, you are actually going to be able to see the recoil here when it drops the balls. When you see that recoil there, the idea is you can land a spacecraft that has an automatic ball thrower or rock thrower on an asteroid, and if it just chucks rocks out into space, then the asteroid will go the opposite direction. Consequently, if any of you are ever astronauts and you're lost in space with nothing but a hammer, you can get back to the spaceship by throwing the hammer in the opposite direction. Physics works. So that's one option. I couldn't find anything scientific to show you there. Another option that has been thrown out is using a tether and ballast system in order to change the center of gravity by attaching a very long tether to the asteroid, and I'm talking 10,000 to 100,000 kilometers, and a small weight on the other end. Doesn't have to be too heavy, 1/10 the size of the asteroid, the mass of the asteroid will do. You can change the center of gravity here at the asteroid, and that will change how the asteroid goes around the sun, because it's the center of gravity, and that will change how it moves. So those are just a couple more extras. So, now that I've scared you with all those, why don't we see asteroids and people running around screaming as much as we do in Hollywood? Well, there's a few very good reasons for that. We believe we found all the asteroids greater than 1 kilometer across, so all the really dangerous ones. The late heavy bombardment period went out of style about 4 billion years ago. This was a very turbulent time in the young solar system, and things have settled down substantially since then. We're looking forward to the next 4 billion years. Things are mostly stable in the solar system. I say mostly because stability is a very tough word with planetary systems, lots of bodies, but things are mostly stable in the solar system. Most of the asteroids we see in near Earth come from, or came from, collisions between asteroids in the asteroid belt. Like I said, average distance between asteroids and the main asteroid belt is 1 million to 3 million miles. So those are leftover debris from collisions a long, long time ago. Collisions, of course, still happen. Things still get moved around in space. We still get perturbations. But for the most part, things have settled down. Right now, the largest threat to Earth that we know of that could cause sub-regional impacts is 2009 FB. What a name. He's about 140 meters across, and he has less than a 0.2% chance of hitting the Earth in 2185. This, of course, means that there is greater than a 99.8% chance that he's not going to hit Earth, and I will take those odds. Now, 80 to 100 tons of asteroid material do hit the Earth every day. This is mostly in form of very, very small dust particles that we go through. So we do hit asteroids, just not these big ones. The bigger they are, the more rare they are. And that's what's seen in this here. I know you can't really read this, but let's all think of our good friends, the dinosaurs, and the great sacrifice they gave. The dinosaurs, we believe, were ended by an asteroid that was about 6 miles across, or 10 kilometers. Here, according to this table from the Australian Academy of Science, we on Earth would see a asteroid of that size hit the Earth every, well, about 150 million years. Now, the dinosaurs were wiped out 65 million years ago. This does not mean that in 75 million years, we are going to see another asteroid that is 6 miles across. What it does mean is that in any 150 million year period, you would only likely see one of these kind of events. Asteroids that can cause global catastrophes, a 1 kilometer, you would only see every about 350,000 years. Longer than, civilization has been around. For your more smaller ones, 90 meters across, about a football field, a little bit less than, you see those every 4,400 years. I don't know what you were doing 2000 BC, but I wasn't that worried about asteroids. So, we are okay. So, yes, asteroids are out there. We do have techniques that we believe we can be used to do with them as long as we find them early. Given a good network of ground-based and space-based telescopes, we believe that it would be possible to get decades warning on asteroids that are 300 feet or larger. So, don't panic.
Questions for Elizabeth?
Yes. Yes, Armageddon was a comet. So what about the comets and not just the asteroids? Well, we hope that our surveys would also catch comets. And all we can do is just keep looking. Just don't panic. Still safe. And Bruce Willis is still around to help us if that one comes along. So.
Wasn't there one just a couple weeks ago? I heard.
An impact. There was an impact a couple weeks ago. Yes, we do have impacts all the time that's happening. We also have air bursts. Sometimes they don't make it all the way to the ground. But again, it's all relative size. These big ones are the ones that we are not likely going to see hit the ground.
So in how many of these scenarios where we deflect the asteroid, blow up the asteroid, how many times, like what's the percentage of Bruce Willis dying in these attempts?
Like 9 out of 10, is it like...
Well, we saw how he did against the nukes. If you're going to crash his spaceship, I'm guessing it's not going to be good. The other ones seem to be fairly mild as opposed to that. So hopefully he has a good chance of surviving.
If you would like combine techniques, like get it out of the way or fix things less than
The question was, by combining different techniques, could we lower the time needed for response? I am not. That is an excellent question. I'm not sure that anybody has looked into combining the different techniques. Unfortunately, at the moment, we have nothing in our back pocket to go out immediately. So if we found something today, I'm sure we would spend a lot of time deciding which one, but we would probably go for Melton. I'm sure by impacting more change in the velocity, we would be able to affect it greater at a shorter amount of time.
If we could do it, if we had a big enough mirror and we could track it well enough, could we heat asteroids up at such a far distance and alter its character?
Could we heat asteroids at a larger distance? That is certainly being looked into right now. They're also looking at arrays of lasers in order to vaporize asteroids. I think they need like 100-meter square array to vaporize a small asteroid. If you had a big enough mirror in space, you might be able to do it. I'm not sure that you could do it from the ground.
Let's thank Elizabeth again.
All right, so we are going to go ahead and start trivia. If you would like to play trivia and do not